Have you ever stopped to think about what actually powers our world? You know, from the gas in our cars to the plastics in our hands, there's this invisible architecture holding it all together. So, what is it? Well, today we're diving deep into the stuff that makes it all possible: hydrocarbons. And yeah, the answer is a surprisingly simple but incredibly powerful class of compounds called hydrocarbons. You can think of them as the architecture of energy. They're this invisible framework holding up so much of our daily lives, and they do it by storing a just massive amount of energy in their chemical bonds.
At their very core, hydrocarbons are, well, they're exactly what they sound like. They're organic compounds made up of only hydrogen and carbon atoms. That's it. But don't let that simplicity fool you, because from this basic two-part recipe comes almost all the complexity and power of modern chemistry.
So how do we even begin to organize them all? It really just comes down to one thing: the bonds between the carbon atoms. We basically split them into two big groups. You've got your saturated hydrocarbons, which only have single bonds, and then you've got the unsaturated ones, which rock double or even triple bonds. And believe it or not, that one little difference is the key to their totally different personality.
Okay, first up, let's talk about the foundation of the family, the alkanes. These guys are the most stable and, honestly, the most straightforward of the bunch. They're defined by having only single carbon-carbon bonds, which makes them the basic and generally pretty unreactive framework of organic chemistry.
So why are they so stable? It comes right down to their structure. See, each carbon atom is what we call sp3 hybridized, which is just a fancy way of saying it forms 4 super strong identical single bonds. This shape naturally pushes all the other atoms as far apart as possible, creating this perfect tetrahedral geometry. With no weak spots, no exposed electrons, they're just not looking to react. That's why they got the nickname paraffins, which literally means little affinity.
But simple definitely doesn't mean boring. Alkanes introduce this absolutely fascinating concept called structural isomerism. This is where you can have the exact same set of atoms, the same chemical formula, but you can arrange them in different ways to create totally different molecules. It's like having the same set of Lego bricks, but building 2 different things.
A perfect example is butane. Both N-butane and isobutane have the exact same formula, C4H10. But look at their shapes. N-butane is a straight chain, giving it a big surface area. That means stronger attractions between molecules and a higher boiling point. Isobutane, on the other hand, is branched and more like a little ball. It has weaker forces between its molecules and, you guessed it, a lower boiling point. Same parts, totally different properties.
Now, that single carbon-carbon bond in alkanes, it's got another cool trick up its sleeve. It can spin. The bond acts like a tiny axle, letting the 2 ends of the molecule rotate freely around each other. These different rotational arrangements have a name. They're called conformations. But this spinning isn't perfectly smooth. When the hydrogen atoms are all spread out, that's called the staggered conformation, the molecule is super stable and at its lowest energy state. It's happy. But as it rotates and the hydrogens line up, they start repelling each other. This eclipsed conformation creates what we call torsional strain, which is a high-energy, unstable state. The molecule is constantly flipping between these two, but it spends almost all its time in that comfy, low-energy, staggered form. So, if alkanes are so stable and unreactive, how do we get them to do anything? Well, one classic way is called free radical halogenation. The idea is to create a free radical, which is a super-reactive atom with an unpaired electron to kick off a wild chain reaction. It all happens in 3 stages: initiation, propagation, and termination.
Let's walk through it. First, you've got initiation. A little bit of sunlight is enough to split a chlorine molecule into 2 crazy reactive chlorine radicals. Then comes propagation. A chlorine radical slams into a methane molecule, steals a hydrogen, and creates a methyl radical. This new radical is just as hungry, so it attacks another chlorine molecule, making our final product, and, this is the key part, a new chlorine radical, which keeps the chain going. The cycle only stops with termination, when any 2 radicals finally find each other and pair up, ending the chain.
All right, so we've covered the stable foundation. But what happens when we introduce more than a single bond? Well, welcome to the world of alkenes, the active builders of the hydrocarbon family. Their secret weapon and their defining feature is that carbon-carbon double bond.
And that brings up a really important question. Why? What is it about having a double bond that suddenly makes these molecules so much more eager to react, especially compared to those chill, stable alkanes?
The answer is all in the anatomy of that double bond. It's actually made of two different parts. You've got a super strong sigma bond, which is like the main structural beam holding the carbons together, but then you have a weaker pi bond, which exists as this fluffy cloud of electrons above and below the molecule. That exposed, vulnerable electron cloud is just an easy target for other molecules to attack, and that's what makes alkenes so reactive. That pi bond does something else too. It stops the bond from rotating. It's rigid, it's locked in place. And this creates something called geometric isomers. When the big groups are on the same side of the double bond, we call it cis. When they're on opposite sides, it's trans. And this tiny spatial difference can totally change a molecule's properties, like making one polar and the other nonpolar.
You can actually see this reactivity in action. It's a classic lab test. If you take some orange-colored bromine water and add an alkene to it, that reactive pi bond immediately breaks open and reacts with the bromine. As the bromine gets all used up, poof, the orange color just disappears. It's a clear visual sign that you've got an unsaturated compound on your hands. Pretty neat, right?
Now, when we try to add something like hydrogen bromide, HBr, to an alkene, things get even more interesting. It turns out the exact product you get depends entirely on the reaction conditions. Let's look at what happens when you run the reaction with and without peroxide.
So this shows off a really key principle. Without peroxide, the reaction follows something called Markovnikov's rule. The easiest way to remember it is the rich get richer. The hydrogen atom adds to the carbon that already has more hydrogens. Simple enough. But if you add a little peroxide, it flips the whole script. You trigger a different mechanism, and the reaction goes anti-Markovnikov. The bromine adds to that same carbon instead. It's a super powerful way for chemists to control exactly what they make.
And finally, let's crank the intensity all the way up with the alkynes. These are defined by a powerful carbon-carbon triple bond, making them the most energetic of the simple hydrocarbons. This triple bond forces the whole molecule into a perfectly straight, linear shape. And it also does something weird. It makes the hydrogens on the end of the chain surprisingly acidic, which gives alkynes their own unique chemical personality.
So when you put it all together, you can see this really clear, beautiful trend. As we go from single-bonded alkanes to double-bonded alkenes and finally to triple-bonded alkynes, that carbon-carbon bond gets shorter and stronger. But at the same time, with each new pi bond we add, the molecule's reactivity just skyrockets. They go from being stable and boring to being these highly reactive, essential building blocks.
In the end, this entire architecture of energy really just comes down to the carbon bond. Is it a stable single bond, a reactive double bond, an intense triple bond? That one feature dictates almost everything: the shape, the energy, the behavior of the molecule. And if you understand that simple rule set, you've got the key to unlocking the chemistry that powers our entire world, which really just leaves one question: what else can we build with it?